All right, guys. Um, Matthew's back here, and we're going to be doing 3.2 on the CSM worksheet. So here we're trying to prove the existence of n such that a to the n is congruent to 1 mod p. And we're told that p is prime, and a is not evenly divisible by p. And so in part A, we're trying to prove that there are at most p minus 1 different values for a to the n mod p. So let's start with the information we're given, right? Under mod p, let's start with under mod p, we have p total different values. And those would be from 0 all the way up to p minus 1. But as we know that p is not divisible by a, as they do not share common factors, no matter how many times we multiply a by itself, it's never going to be divisible by p. Like this is never going to happen. So, as we know that 0 is not a possible number, but while 0 isn't a possible number, all of the other numbers are still possible. So if we have p possible different values, and then one of them is not possible, that means we now have p minus 1 possible values for um, a to the n mod p. So that is A. Now let's move on to B. In B, we have to argue that there must be some ij such that a to the I is congruent to a to the j mod p. And we're told that we should use our result from part A as a hint. So thinking of the possible unique powers that we can have under mod p, right? The total possible number of powers we can have is just going to be um, the p possible different values under mod p. So that's just going to be, you can think of it as like 0 to p minus 1, or 1 to p. And for this sake, or for this case, we'll use 1 to p to represent the p possible different values. And for the total possible values, I'll call them the results, the possible results we can have under mod p. And this is going to be using part A. We can only have p minus 1 possible values. So if we can see that we have p possible values of powers and p minus 1 possible values for the results, right? The intuition here is going to be that we are going to think of the pigeonhole principle, and that um, if we have p possible powers and p minus 1 possible results, there's got to be some results that is the same for two different powers. And that's kind of what we have here with a to the I being congruent with a to the j mod p. That's exactly what we're saying. So now we're going to say that as we've chosen to say, like, we're representing all of our possible powers of 1 to p, that we'll say that for some, we'll say that j is greater than I has to be at least 1, and j is at most p to represent the p possible values, and that, yeah, using the pigeonhole principle, we have shown that we have p possible values of powers, p minus 1 possible values of results. Therefore, one of those results has to be the same for two different powers, which is I and j. So now we're going to use part B here to prove that there exists some n such that a to the n is congruent to 1 mod p. So here, what we're going to do is use what we had above, right, where we proved that there's some, there are going to be two different values of powers that are going to have the same resulting value under mod p. And what we're going to do here is kind of use some algebraic manipulation to prove that this works. So we know that a to the I is congruent to a to the j mod p, but this is also can also be written as if we just subtract ai from both sides, a to the j minus a to the I, which is also just a to the j minus I guess. It's true. A to the j minus a to the I is congruent to 0 under mod p. Wait, never mind. Let me just erase that. So what we're going to do from here is we are going to rewrite it out. We know that is true. And as these are both like kind of what we did earlier, I erased that, I did a little bit early. But what we can do is they're both powers of a. We can factor out an ai here, and then we just have, as we know, as we earlier said that j is greater than I, we just have a to the j minus I minus 1. And as we know that a is not divisible by p for any power of a, we know that this isn't true. This by itself isn't true. So that means that this being divisible by p has to be true. Just properties of mod, right? We can have like one thing that's not a multiple, but if it's multiplied by another thing that's a multiple, then that works under mod space. So we know that p is divisible by a to the j minus I minus 1. And then if we kind of just rewrite this back using mod, we then have that a to the j minus I is congruent to 1 mod p. And now we've proved that there is some n where n is j minus I that has a to the n being congruent to 1 mod p hold, that used kind of what we had from B, which built off what we had from A. And that's the entirety of 3.2. See you next week.